Every single car you drive today contains technology that was, at some point, considered too advanced, too expensive, or too dangerous for anything other than a 200-mile-per-hour racing machine. That is not marketing language. That is engineering history. Formula One has quietly been the research and development engine behind your everyday driving experience for over 7 decades, and most people have absolutely no idea how deep that connection runs. In the next 10 minutes, you are going to discover exactly how the most extreme motorsport on the planet has shaped the car sitting in your driveway. We will trace the journey from the pit lane to the production line, covering everything from carbon fiber and aerodynamics to hybrid systems and tire technology. And we will get to the one transfer that nobody in the mainstream automotive world likes to admit because it challenges the entire narrative about who really drives innovation in this industry. Stay with us. Formula One was born in 1950 as a regulated international motorsport competition, but its roots as a technology laboratory go back even further. The earliest Grand Prix cars of the 1930s were already pushing boundaries with supercharged engines, lightweight alloys, and suspension geometry that engineers in road car factories were only beginning to dream about. When the modern World Championship era began, constructors like Ferrari, Mercedes, and BRM were simultaneously building race cars and road cars, creating a direct pipeline of ideas between the track and the street. That pipeline has never closed. What has changed is the speed at which technology travels through it. In the 1960s, the journey from race technology to road car could take 15 to 20 years. Today, with modern manufacturing techniques, computerized design tools, and globalized supply chains, that timeline has compressed to as little as 3 to 5 years. Some technologies make the jump even faster. And the financial scale of this transfer is staggering. Analysts at Deloitte estimated in 2022 that the Formula One industry generates over $6 billion in annual economic activity, with a significant portion of that investment eventually flowing back into consumer automotive development. Let us start with the most visible example, the paddle shift gearbox. Before 1989, every racing driver and every road car driver changed gears using a traditional H-pattern stick shift. Then Ferrari introduced the first semi-automatic paddle shift transmission in Formula One at the Brazilian Grand Prix. Ayrton Senna hated it initially, but within 2 seasons, every team on the grid had adopted the technology. By the mid-1990s, road cars began offering semi-automatic options. By the 2010s, the traditional manual transmission had effectively disappeared from mainstream vehicles. Every time you pull a paddle behind your steering wheel, you are using a direct descendant of a technology developed for a race car. Carbon fiber is another story that almost nobody tells correctly. When McLaren introduced the first carbon fiber monocoque chassis in 1981 with the MP4/1, it was genuinely revolutionary. The material was lighter than aluminum, dramatically stiffer, and far more energy-absorbing in crashes. It took nearly 20 years before carbon fiber became cost-effective enough for mass-production vehicles. Today, BMW uses carbon fiber reinforced plastic in the structural components of the i3 and i8. Lamborghini builds entire passenger cells from it. Ford uses it in the GT supercar. The techniques developed to manufacture and repair carbon fiber quickly and reliably in Formula One directly informed how automotive manufacturers learned to work with the material at scale. Regenerative braking is where the story gets particularly interesting, and this is where we place our mid-roll brake. When you drive a hybrid or electric vehicle and you lift off the throttle or press the brake pedal, the electric motor runs in reverse, converting kinetic energy back into electricity. This feels completely normal today. But this technology was refined and proven under the most punishing conditions imaginable, Formula One competition, before it ever reached your commute. The KERS system, which stands for Kinetic Energy Recovery System, was introduced to Formula One in 2009. Teams were allowed to recover energy under braking and deploy it as an electrical power boost of around 80 horsepower for a limited time each lap. The engineering challenges were immense. The systems had to survive extraordinary heat, violent vibration, and the stresses of 35G cornering forces. Every hybrid system in your Toyota, your Honda, your BMW, your Ford is a direct beneficiary of that brutal development program. But here is what nobody talks about. The current Formula One hybrid units, known as power units since 2014, are the most thermally efficient internal combustion engines ever built by human beings. They achieve over 50% thermal efficiency, meaning they convert more than half of the fuel's energy into useful power. Your average road car engine operates at roughly 30 to 35% thermal efficiency. The gap is enormous, and closing it even partially is the entire engineering mission of companies like Toyota and Honda, who invest directly in Formula One partly as a real-world laboratory for these efficiency gains. Now let us talk about aerodynamics, because this is where the influence gets subtle but universal. In the early days of automotive design, cars were styled, not engineered for airflow. By the 1970s, Formula One teams had discovered ground effect, the principle that carefully shaped underbody tunnels could generate enormous downforce without adding drag. This understanding of how air behaves around moving objects fundamentally changed how road cars were designed. Today, every production vehicle goes through hundreds of hours of computational fluid dynamics simulation and wind tunnel testing. The drag coefficients on modern electric vehicles, like the Tesla Model 3 at 0.23 CD or the Mercedes EQS at an astonishing 0.20 CD, are direct results of aerodynamic disciplines that Formula One made mainstream. Tire technology is another direct transfer with real safety consequences. Pirelli, Michelin, Bridgestone, and Goodyear have all run Formula One programs, and every compound development, every understanding of thermal behavior, every insight into how rubber deforms under load at extreme speed has fed directly into the tires on your road car. Michelin's Pilot Sport range, which equips millions of performance road cars, is explicitly developed using Formula One data. The grip levels that drivers now take for granted on wet roads in particular owe an enormous debt to decades of race tire research. Electronics and software represent perhaps the largest but least glamorous area of technology transfer. Modern Formula One cars generate over 1,000 data channels simultaneously. Teams analyze terabytes of information from every session. The sensor technology, the data processing algorithms, the predictive modeling, all of this has migrated into the automotive world. Your car's electronic stability control, traction control, and anti-lock braking systems all share conceptual DNA with systems first developed and refined in motorsport. The McLaren Applied Technologies division, which grew directly out of the Formula One team's engineering culture, now provides control systems and battery technology for road vehicles and even public transportation. And then there is safety. This is where Formula One's contribution becomes genuinely profound. The HANS device, Halo cockpit protection, advanced energy-absorbing barrier systems, crash structure design, all developed and proven in racing conditions, have been adapted by road car manufacturers and safety regulators globally. The crumple zone technology in your car was influenced by racing crash structure research. The fire suppression materials in modern vehicles trace their lineage to fireproof racing suits and cockpit materials developed after tragedies in motorsport. Forced engineers to find better solutions. The pattern here is consistent and it is important. Formula One operates at the absolute edge of what is physically possible, with engineering resources and competitive pressure that no road car manufacturer can replicate internally. That extreme environment accelerates development, proves concepts under the most demanding conditions imaginable, and creates intellectual property and material science knowledge that then filters into mainstream production. The lag time is shrinking every decade. The next major wave is already visible: solid-state battery technology, advanced torque vectoring, predictive chassis systems that respond to road surfaces before the driver even notices them. All being developed right now in motorsport contexts. All heading for a driveway near you within a decade. Formula One is not just a sport. Before you go, if you learned something valuable today, hit that like button right now. Subscribe to AutoVision Daily for a brand new video every single day. We will see you in the next one.